24 stone boxes sit inside a tunnel cut into the bedrock at Saqqara, sealed off from sunlight for most of the last 4,000 years. Each one weighs as much as 100 tons. Each one is carved from a single block of granite, with walls so flat and corners so square that a flashlight run along the edge barely shows a gap. Granite is not soft stone. It is built from quartz and feldspar, two minerals hard enough to scratch a steel blade, and it does not forgive a careless tool. Cutting it cleanly, with right angles and polished interior walls, is a serious engineering problem even now. With diamond saws and water-cooled blades, the people who built these boxes did not have any of that. According to the tools we have found in their workshops, they had copper, wood, stone, and sand. And somehow, that was enough to produce work this precise. That gap between the tools we know they had and the results sitting in that tunnel is the real mystery, and it has been argued over by actual engineers and actual archaeologists for more than 100 years. Not online conspiracy threads. Published papers, side-by-side experiments, and one very famous, very contested chunk of drilled-out granite that still sits in a museum case in Cairo. Stay with me, because the answer is stranger and more grounded than most of what gets said about this online. Picture standing inside that tunnel yourself. The air is cool and still, the kind of stillness that only exists underground, sealed away from wind and sun for thousands of years. The boxes line both sides of the corridor like a row of stone vaults, each one big enough to park a small car inside, each lid weighing tens of tons on its own, somehow still resting in place, still fitted to its box with barely a gap you could slide a coin into. Run your hand along the inside wall of one of these boxes, and the surface feels almost polished, cool and smooth, with none of the pitting or unevenness you would expect from a chisel dragged by hand. Whoever finished this stone was not rushing, and they were not guessing. Every surface suggests a controlled, repeatable process, applied the same way, over and over, box after box, for what scholars believe was a span of centuries. That consistency is itself a clue, and it is the first thing any real investigation has to explain. Not just how one box got made, but how an entire culture kept making them, generation after generation, without the process drifting, degrading, or disappearing. Start with what is not in dispute. The ancient Egyptians left behind drawings of their own stoneworkers. These are not vague symbols open to creative translation. They are detailed wall reliefs, painted in full color, found in the tombs of officials who personally oversaw royal workshops. The most famous set comes from the tomb of a man named Rekhmire, who served as vizier, essentially the prime minister, under Pharaoh Thutmose III in the 15th century BCE. His tomb walls show, in registers stacked one above another, men working metal, men polishing stone vessels, and men drilling. One scene shows two workers operating a tall drill shaft with a heavy weight near the top, leaning their body weight into it while another man works the crank. That weight is doing a job. It is converting the worker's effort into steady downward pressure on a rotating bit. The same basic principle a modern drill press uses, just powered by human muscle instead of a motor. This is one of the actual hieroglyphic and pictorial records the title of this video is talking about. It does not show a power source nobody can explain. It shows ordinary people using a clever, weighted, hand-cranked drill, and it tells us something specific. Pressure plus rotation. Sustained over a long time was the method. The question that has kept engineers arguing for a century is whether pressure and rotation, applied only by human strength, can actually explain the precision sitting in that tunnel at Saqqara. Rekhmire's tomb is not the only place this kind of evidence survives. Other Old and New Kingdom tombs around Giza, Saqqara, and the Theban necropolis show similar scenes. Men working a simple bow drill, the bowstring wrapped around a vertical shaft and pulled back and forth like sawing a violin, spinning a stone or flint-tipped point against a smaller block. Other reliefs show craftsmen polishing finished stone vessels with handheld rubbing stones, working in pairs, one steadying the piece while the other grinds. None of these images are vague symbols requiring a creative or convenient translation to mean something exotic. They are straightforward depictions of a known toolkit, drawn by people who watched the work happen and wanted it remembered for eternity. That detail matters more than it might seem. It cuts directly against the idea that the real method was ever hidden or secret. The Egyptians were not shy about showing their craftsmen at work. They carved these scenes into the walls of tombs meant to last forever, displayed proudly, the same way a modern company might frame a photograph of its own factory floor for visitors to see. If there had been some more dramatic machine involved in cutting the hardest stone in their world, a civilization this obsessed with permanence and legacy had every reason to put it on the wall, not bury it in a single word found nowhere else. Here is why the question will not go away. Granite sits at roughly 6 to 7 on the hardness scale used by geologists, depending on its mineral mix. Copper, the main metal tool available in the Old and Middle Kingdoms, sits at around 3. In a straight fight, copper loses to granite every time. A copper blade dragged across granite does not cut it. It just wears down the copper. So if copper was the tool, copper could not have been doing the actual cutting. Something else had to be doing the work, and the copper had to be a delivery system for that something else. This is where sand comes in. Quartz sand, the same material that makes up a large part of granite itself, sits at around 7 on that same hardness scale. Pack quartz sand into the moving point of contact between a copper blade and a block of granite, and the sand becomes the actual cutting edge. The copper saw, or copper tube, becomes a frame that holds the abrasive in place and keeps moving it across the stone. It is slow. It takes enormous patience and enormous labor, but mineral against mineral, hardness wins over softness every time, and quartz sand is hard enough to grind granite down, grain by grain, if you are willing to keep at it long enough. That is the mainstream explanation, and it is not a guess pulled out of nowhere. It has been tested. There is another piece of physical evidence that points the same direction, and it comes straight off the most famous granite object in Egypt, the empty sarcophagus inside the king's chamber of the Great Pyramid. Long, straight saw marks run across one corner of that box, marks Petrie himself measured and photographed. If you assume the saw stayed perfectly straight for its entire stroke, the geometry of those marks implies a blade somewhere in the range of 8 or 9 feet long, almost certainly with hard cutting points, possibly flint or some harder stone, set into the copper edge the way a modern hacksaw sets replaceable teeth into a steel frame. Nobody has ever found one of these saws intact. Copper does not survive well in the ground, and a tool that valuable would likely have been melted down and reused long before anyone thought to bury it for archaeologists to find later. But the marks left behind are consistent, repeatable, and exactly the kind of signature a long, abrasive-fed saw would leave on stone, worked back and forth by several men standing along its length, the same way 2 people might work a 2-man crosscut saw through a tree trunk today. In the early 1880s, a British engineer and archaeologist named William Flinders Petrie spent months at Giza measuring everything he could get his hands on, with a level of obsessive precision that nobody had applied to the site before. Petrie did not just look at finished monuments, he collected the waste. Among the debris around the pyramids and temples, he found something most visitors would have stepped over without noticing: a core of granite drilled out from a larger block with a tight spiral groove running around its surface. That spiral told him something important. It was not random scratching. It was the signature of a rotating tool cutting in a continuous, controlled path, the exact pattern you would expect from a tube drill turning steadily under pressure while abrasive grains did the cutting. Petrie measured the spacing of the spiral and used it to estimate how much material was being removed with each rotation. The number he calculated startled him. It implied the tool was advancing through solid granite at a rate that seemed too fast for hand pressure alone to explain, especially using nothing harder than copper and sand. Petrie did not claim ancient Egypt had hidden machines. He was cautious, and he said so in his own writing, but he also refused to pretend the problem wasn't there. He suggested the abrasive might have included something harder than ordinary sand, possibly fragments of a harder mineral mixed in, essentially primitive jeweled cutting points. He put the puzzle on the table and basically dared the next generation of researchers to solve it properly. For decades, almost nobody did. That changed in 2003 when an archaeologist and experimental researcher named Dennis Stocks decided to stop arguing about the theory and just build the tools. Stocks recreated copper saws, copper tube drills, dolerite hammerstones, and wooden bow drills using only the materials and metallurgy that would have existed in ancient Egypt. Then he used them, by hand, on real granite for years and recorded exactly what happened. His findings were detailed enough to fill a full academic book: Experiments in Egyptian Archaeology, Stoneworking Technology in Ancient Egypt. Copper blades and tubes, fed with quartz sand and kept under steady pressure, did, in fact, cut granite. Slowly. A long sawing or drilling session might advance only a fraction of an inch, but it worked consistently, and it produced surface marks that matched what archaeologists actually find on ancient Egyptian granite artifacts: straight saw lines, spiral drill grooves, and rough, slightly pitted interior surfaces consistent with abrasive grinding rather than a smooth, melted, or vibration-polished cut. Stocks also tested heavier stone hammers, specifically dolerite, a volcanic rock harder than granite, and found that simply pounding granite with dolerite balls over and over could rough out a shape long before any saw or drill touched the fine details. None of this required electricity. None of it required a mystery power source. It required time, organization, and a labor force large enough and patient enough to grind through stone the way water grinds through rock, just on a human timescale instead of a geological one. And that labor force is not a guess either. In the 1990s, archaeologists Mark Lehner and Zahi Hawass excavated an entire workers' settlement just south of the Giza Plateau. Barracks-style housing, large communal bakeries, evidence of cattle and fish brought in to feed thousands of people, and administrative buildings for managing it all. This was not slave labor in the way popular imagination sometimes pictures it. The evidence points to organized, rotating crews of laborers, fed, housed, and apparently treated well enough to be buried with respect near the monuments they helped build. Even earlier, in 1837, the engineer Richard Howard Weiss forced his way into sealed relieving chambers above the king's chamber using gunpowder and found something nobody expected: painted quarry marks and crew graffiti left by the work gangs themselves, informal labels with names like Friends of Khufu, scrawled onto blocks never meant to be seen again once the pyramid was sealed. That graffiti is, in its own way, a more human kind of hieroglyph than anything in this debate. It is not a polished royal inscription. It is workers signing their crew's name on a block before it disappeared into the structure forever, the ancient equivalent of construction workers signing a steel beam before it gets covered in drywall. Put together, the bakeries, the housing, and the graffiti tell you exactly what kind of machine was really doing this work. Not a mechanical device, but a large, organized, well-fed human workforce, broken into competing crews, grinding through stone year after year as a matter of national priority. So why does the argument keep coming back? Because Stokes proved the method could work. He did not prove it was fast enough or precise enough to fully account for every single piece of granite work the Egyptians left behind, especially the most extreme examples. That gap is where Christopher Dunn comes in, and his name is worth knowing because he is a real figure in this debate, not an anonymous internet voice. Dunn is a master machinist and mechanical engineer with decades of hands-on experience cutting metal and stone using industrial equipment. In 1983, he traveled to the Cairo Museum and personally examined the same type of drilled granite core that had troubled Petrie a century earlier. Using his own professional background in machining, Dunn calculated the downward force he believed the drill bit would have needed to cut at the rate the spiral grooves suggested, and arrived at a number, in his estimate, equivalent to roughly 2 tons of pressure concentrated on a narrow drill tip. That is an enormous load for a hand-operated tool to sustain evenly, and Dunn argued that no muscle-powered drill, no matter how cleverly weighted, could apply that kind of sustained, perfectly even pressure without the bit wandering, snapping, or gouging unevenly into the stone. From there, Dunn proposed that the Egyptians, or whoever cut that particular core, were using some kind of high-speed, high-power rotational tool, and in later books, he went much further, suggesting the Great Pyramid itself may have functioned as a kind of energy-generating structure. That second claim, the power plant theory, is not supported by mainstream Egyptology, mainstream physics, or mainstream archaeology, and most serious researchers, including many who respect his machining background, consider it well outside the evidence. But the narrower observation that started it, the question of whether unaided human power can really explain every drilled granite core in the archaeological record, has never been fully closed, and that is the honest, ongoing tension at the center of this whole debate. One camp says the variation in ancient drilling speed, evidenced by cores that show faster and slower advance rates side by side, simply reflects different workers, different pressure, different abrasive grain size, and different amounts of time spent, all entirely explainable by hand methods. The other camp says some of the recorded advance rates are difficult to reconcile with any hand-powered method we have successfully tested. Full stop. Both sides are working from the same physical object. They are reading the same spiral groove and reaching different conclusions about what force produced it. It is worth pausing on why the vibration idea sounds plausible at all, because the underlying physics is real, even if its application here is speculative. In modern industry, ultrasonic machining genuinely exists. A cutting tip vibrating tens of thousands of times per second, paired with an abrasive slurry, can shape extremely hard materials like glass, ceramic, and tungsten carbide, with very little of the subsurface cracking you get from a straightforward grinding pass. That is established. Mainstream engineering, used in factories today. The leap some online claims make is assuming that because this technique exists now, and because some ancient granite surfaces look unusually clean, the ancient Egyptians must have had an equivalent of it then. But ultrasonic machining requires a power source capable of driving a tool at that frequency, consistently, for as long as the cut takes. And nothing resembling that has ever turned up anywhere in the Bronze Age archaeological record. Not in Egypt, not in Mesopotamia, not anywhere else on Earth. No batteries, no wiring, no magnets, no mechanism remotely capable of generating or storing that kind of sustained high-frequency energy. An idea can be physically real and still have zero supporting evidence for its presence in a specific place and time, and that is exactly where the ultrasonic hypothesis sits. It explains the clean cuts neatly. It has nothing else behind it. There is also a wider geographic point that often gets flattened into a tidier story than the evidence supports. Hard stone work shows up at the Khafra Valley Temple at Giza, in granite columns and shrines at Karnak, and scattered through other sites across many centuries, and the quality is not uniform. Some surfaces are exceptionally fine. Others, from the same general period, are noticeably rougher, with visible tool chatter and uneven joints. That unevenness is exactly what you would expect from skilled human teams of varying experience, working under varying deadlines and varying levels of royal funding. not from a single, perfectly consistent machine that operated at one fixed standard for a few centuries and then vanished everywhere at once. Precision in ancient Egypt rises and falls with the wealth, stability, and ambition of whichever dynasty was paying for it. The same pattern you would expect from human institutions, and a very different pattern than you would expect from a single lost technology with a single on-off switch. Now bring in the most dramatic single piece of evidence in this entire story. The unfinished obelisk, still lying in its quarry bed at Aswan. If it had been completed and raised, it would have stood taller than almost any obelisk the Egyptians ever finished, more than 1,000 tons of single-piece granite. A column of stone roughly the height of a 7-story building, meant to be hauled to a temple, stood on end, and left standing for eternity. Instead, it never left the ground. You can walk the entire length of it today, and the surface tells the whole story without a single word of explanation needed. Archaeologists who excavated the site in the 1920s found the surface covered not in smooth saw marks, but in thousands of small, shallow, rounded depressions. The unmistakable signature of repeated pounding with hand-held dolerite hammerstones, each blow only removing a tiny chip of granite, multiplied across millions of strikes by dozens of workers over what would have been months of brutal, repetitive labor. This was not a delicate, high-precision cutting process. It was crews of men crouched along the stone in the heat, battering the granite down a few grains at a time, until the rough shape of the obelisk slowly emerged from the surrounding bedrock, the way a sculptor might rough out a figure before the fine detail work even begins. And then, partway through, the work simply stopped. Cut into the stone itself are deep cracks, fractures running through the granite that no amount of skill or effort could repair. Whoever was supervising that project made the only sensible call available: abandon a flawed monument rather than risk losing it or risk lives, trying to force a cracked 1,000-ton stone free from the quarry. The obelisk was left exactly where the crack appeared, a frozen snapshot of an active work site, and it has sat untouched in that same spot for roughly 3,500 years. There is no mystery about why the work ended. The stone itself, fractured straight through, tells you. The real significance of the unfinished obelisk is not a hidden machine. It is the opposite. It is direct, physical proof of exactly how punishing and exactly how manual the process really was. Full crews, pounding stone with stone, for as long as it took, and sometimes losing the project anyway, to a flaw nobody could see until it was too late. Put these three pieces of evidence side by side and a clearer picture starts to form, one that is more interesting than a simple yes or no answer. The tomb paintings of Rekhmire and other officials show us the basic toolkit: weighted, crank-operated drills, powered entirely by human effort, applying steady pressure over time. The experimental work by Dennis Stocks proves that toolkit, paired with copper and quartz sand abrasive, can physically produce the saw marks, the drill grooves, and the surface texture found on real Egyptian granite artifacts, without requiring anything beyond Bronze Age technology. And the unfinished obelisk at Aswan proves, in the most visceral way possible, just how much raw, repetitive human labor that process actually demanded. Because we can see the unfinished pounding marks with our own eyes. Where the debate stays genuinely open is in the outlier cases. The small number of measured drill cores and cut surfaces, where the implied speed and force, by some calculations, sit at the upper edge of or beyond what controlled hand power experiments have so far reproduced. Christopher Dunn's challenge from 1983 has never been definitively answered in either direction. Nobody has proven his 2-ton force estimate is wrong. Nobody has proven it is right either, because nobody has run a large-scale, fully controlled modern recreation specifically targeting that exact core, with the kind of rigorous instrumentation that would settle it once and for all. That is not suppression. That is simply a narrow technical research question that has never attracted the funding, the museum access, and the cross-disciplinary team needed to finish it properly. It sits in the gap between Egyptology, which studies the culture, and mechanical engineering, which studies the forces, and very few researchers have ever had deep training in both. There's one more piece of this puzzle worth knowing, because it changes how you should think about the word mystery here. Ancient Egypt left behind an extraordinary written record for an early civilization: ration lists, labor rosters, shipping logs, even daily journals. In 2013, archaeologist Pierre Tallet discovered the oldest papyrus ever found in Egypt at a site called Wadi El Jarf, a logbook kept by an official named Merer, dated to the reign of Khufu, the pharaoh who built the Great Pyramid. The diary records, in precise administrative detail, the movement of limestone blocks from quarries to the Giza construction site, trip by trip, almost like a shipping manifest. It is a genuinely remarkable document. It is also notably about limestone, the relatively soft stone that makes up the bulk of the pyramid's body, not granite, the much harder stone reserved for the most important structural and ceremonial elements, like the king's chamber and the great sarcophagus boxes. We do not currently have an equivalent granite-specific labor log, naming crews, tools, and timeframes for the hardest stonework, the way we do for limestone transport. Does that mean the granite cutting happened in secret, outside the normal chain of command, performed by people who left no records because they weren't really part of the workforce, like some online claims suggest? Almost certainly not. The far more boring, far more likely explanation is the one historians give for gaps like this constantly. Papyrus is fragile, organic material, and the vast majority of ancient Egyptian paperwork simply did not survive 4,000 years of heat, humidity, insects, and time. We have the limestone log because one extraordinary accidental discovery at one specific site happened to preserve it. We are missing other logs on other materials from other workshops, for the same reason most ancient writing in general is missing. It rotted, burned, or crumbled long before anyone today was born to read it. An absence of a record is evidence of nothing on its own. It only becomes meaningful if you can show the record should have survived and somehow specifically didn't, and nobody has shown that here. So where does that leave the actual answer to the question in the title? The hieroglyphs and tomb reliefs that genuinely exist, the ones you can see today on real tomb walls in Luxor, show ordinary craftsmen using weighted, hand-cranked drills and saws. The granite itself, examined up close by engineers and archaeologists for more than a century, shows saw marks and spiral drill grooves consistent with copper tools, driven by quartz sand abrasive, exactly the kind of marks Dennis Stocks reproduced by hand in his own experiments. The unfinished obelisk at Aswan shows, in raw, physical form, just how much grinding, pounding human labor that process really required, and how easily it could still fail despite all that effort. And the one piece of this debate that remains genuinely, legitimately unresolved is narrow and specific. Whether the very fastest, most extreme drilling examples in the archaeological record sit comfortably within what hand power can achieve, or whether they hint at some refinement of method, some detail of technique, tool design, or organization of labor that has not yet been fully reconstructed by modern experiment. That is a real open engineering question, argued by credentialed people on both sides, using real measurements. It is not evidence of lost ultrasonic machines, hidden power plants, or a vanished energy source erased from history by a cover-up. It is evidence that ancient Egyptian stoneworkers operated extremely close to the outer limit of what their technology allowed, close enough that, even now, with modern tools and modern measurement, we are still working out exactly how they pulled it off. And maybe that is the more impressive story anyway. Not a secret machine handed down from someone or something outside the historical record, but a civilization of ordinary people, generation after generation, refining a brutally difficult, brutally physical process until they could shape some of the hardest stone on earth into walls flat enough, corners square enough, and surfaces smooth enough to still make modern engineers stop and stare, 4,000 years later, standing in a tunnel at Saqqara with a flashlight, checking the gap at the corner of a 100-ton granite box and finding almost nothing there at all. The mystery was never about where the power came from. The mystery is how far human patience, human organization, and a few pieces of copper and sand could actually go. Think about what that really means for a moment. Every box in that tunnel, every drilled core in that museum case, every saw mark on that sarcophagus represents thousands of hours of a real person's life. Kneeling on stone, dragging a blade back and forth, feeding sand into a cut by hand, day after day, for a result they themselves might never live to see completed. No pharaoh, no priest, and no engineer of that era needed a hidden power source to leave behind work this precise. They needed exactly what the tomb walls, the workers' village, and the crew graffiti all describe in plain sight. Organized teams, fed and housed and given a task, applying the simplest tools available with a level of patience that modern life rarely demands of anyone. That is not a smaller story than a lost machine. In some ways, it is a larger one, because it does not require us to imagine a vanished civilization smarter than our own. It only requires us to take seriously how much an ordinary group of determined people can accomplish when they have enough time, enough discipline, and enough reason to get it exactly right. The honest answer to the question in the title, based on everything anyone has tested, measured, and reproduced so far, is further than almost anyone, then or now, would have guessed, and it was achieved by hands, not by hidden energy. That is what the hieroglyphs actually show, and it has been sitting in plain sight the entire time.